Yeah, hello. Thanks for having me again. Yeah, SREcon is really a special conference for me. Like my first talk at a conference was at SREcon, and I've come back since a few times. And this talk is particularly special to SREcon because it's essentially a reply or a tangent of a workshop I attended last year, which was run by Liz Fong-Jones, who's sitting here, Krista Bennett, and Stephen Throne, all from Google. And they had a session about doing all kinds of SLOs and giving you best practices. And I remember that very vividly. When I came out of that session, I was, a few things clicked for me. But especially these subtleties with latency SLOs, there was like really a learning I took from there. I was sitting in my Circonus point of view for a long time because we had our take on how to do latencies and have some tools. I will describe them. And then if you are outside that bubble, the complications are different, and particularly with latencies, it's subtle. And so this talk is basically an elaboration on the tangent on last year's SREcon. But I still hope, because the topic is so relevant and in certain sense so basic, that it's valuable for you. So the question this whole talk is about is it's actually like pretty basic. So here's an example of this question. How many requests in August were served within 100 milliseconds? So I'd like you to think of any API that you might monitor or might care about. Can you answer that question? Which raise of hands, if you can. Okay, there, if you want. Okay. So what about 150 milliseconds? Still one or two. 180? Maybe June 16th, 9:12 to 9:35. How many requests were served within 100 milliseconds? See one hand. Here, one other hand. Very, very nice. Okay. So for one of those people who raised their hand, how are you actually doing it? Sorry? Louder. External monitoring service gives you that data. How many requests were there? Okay, but it's about all requests that were served. With, sorry? If you have set it up properly. Yeah. Yeah. So I will talk about how to do it, but this is surprisingly hard to do. Most of the time when I ask this question, I get the answer, well, we have Splunk running back to June, and we have just all the logs, which is also a valid way to do it. Yeah, this is the obligatory slide about myself. As was already mentioned, I'm working as a data scientist at Circonus. I realized I might be one of the very few data scientists at this conference. So yeah, my background is from mathematics, and yeah, as already mentioned, I used to talk about statistics and how to apply it to the SRE field. This is a picture of my pile of firewood. I recently moved to the countryside, and this is the main reason, so I can do more wood chopping. Yeah, this is supposed to be funny. Yeah, so probably this is a brief agenda on why monitor latency, what's an SLO. I can take that brief, and then I will give you three methods how to do it. So why monitor latency? Latency is like the key performance indicator for any API. And if you look at the Google SRE book, they wrote the book on it, then they have the 4 golden signals in it. It's latency, and this is what we are doing here, traffic, errors, and saturation. And that, so latency is the #1 golden signal. So, okay, people care about that. And then this 4 golden signals got later like reshuffled into the red method for monitoring APIs, which is requests, errors, and duration. And duration is just another name for latency. So you might have heard that before, but it made its way to an acronym. So what is an SLO? That's also pretty much from the workshop, and you probably already know that, but it doesn't hurt to say it again. So an SLO or an SLA it comes in 3 different forms. The first is the service level indicator, which is typically a metric. that quantifies the reliability of your service. So typically it has the form of good events versus divided by valid events by 100. So good event might be something like your service was up at a certain point of time. And the server objective then is measured against an SLI and sets some expectations about the server performance. And then an agreement is, service level agreement is what happens if an SLO is not met. And to make that really plastic is once a minute you SSH into a target host and report 1 if it's working and 0 if it's not. An uptime SLO would be 99.9% uptime. So for every measurement you did over the last month, you look if the metric was reporting 1. And if it did so 99.9% of the time, then your SLO was met. And an SLA would be, if you didn't meet the SLO, we will get exactly 1 cake. So that would be a thing. Maybe you have other kind of punishments, but or stuff that happens. Maybe nothing happens, but still good to have the SLO at least. So let's look at the latency SLO example from last year's workshop. That was phrased as follows. So the SLI we were looking at was the proportion of valid requests that were served within 1 second. And the SLO was 99% of valid requests in the past 28 days are served within 1 second. That kind of seems to be following the pattern. But now we have a look at the data which could try to be used to answer that question. And you have the slide here. You see the 99th percentile at the very top, and the y-axis has milliseconds on it. So 1K is the threshold we're interested in. So what does this graph tell us? This graph tells us, well, most of the time, the SLO was met. Like 21st of June, we are mostly below this 1K line. And it's very, very tempting to just say, well, let's smooth out that line and just take a visual average. And I think it should come just below the 1K line if I do the visual averaging. And so I'm led to believe, well, 99% of my requests in the past 28 days are indeed served within 1 second. So that's probably also true for that service. It looks like a very, very well-behaved service. I mean, my services look usually more like this when I put a P90 on it. Because, yeah, I mean, sometimes there's just no load on that API. And it's just nighttime and nobody listens. And so the values go everywhere. So the important bit of information that is missing here is how much traffic was served at each point in time. So if I told you that like, overall the traffic was very flat, very low, and you had good percentiles, but at this spike, basically all of your data came in, then suddenly your judgment of was the SLA met or not would change. And actually the case is, based on this data, you have no way to decide if the SLA was met or not. And that's subtle. And yeah, that's the other thing. I mean, usually if you look at data like that, it's not even close. I mean, you wouldn't actually think you could decide this question if you looked at data which looked like that. So, so the upshot here is percentile metrics are not suitable for calculating latency SLOs. So for latency SLOs, we need to aggregate data across multiple weeks and also across multiple nodes. So you might have 5 web servers which serve requests, but your SLO is over the whole service. You don't have an SLO for node 1, for node 2, and node 3. So you need to do the aggregation across nodes and across long time periods. And both are, like with percentiles, problematic. And then there's another story I can tell in this context, which is from Monitorama a few years back, where I gave a different talk, but on also a latency topic, and then, or actually it was the statistics for engineers class. And then was a guy called Dan Slimman who took that to Twitter and said, well, Heinrich said you can't aggregate percentiles, and probably had that argument a few times, so he clapped there. And then John Rouser came in, which is a data scientist at, I believe, Snapchat, and said he gets annoyed. And then I said, well, it's complicated. And then he said, you can actually average percentiles. And he wrote actually a 10-page blog post here. So he did all kinds of like sampling, and then wow, and he said, well, it's actually, yeah, it actually is not that bad. So in many cases, you can actually, yeah, I mean, I don't have a quote, but his basic take was, well, it's possible. Well, and I said, well, yeah, it might, but if you look in practice, you can get 300% errors. And I don't even have to make data which is very artificial. And that somehow settled the argument. We said, well, yeah, okay, it's quite easy, in fact, to find examples where it completely breaks down. So the point is, if your service is well behaved and you are actually having like 5 web nodes which have all the same load and the load balancer is working, then you can average the percentiles and you will get a very good approximation. And this is basically what John was saying. If you're sampling stuff from the same distribution and then averaging stuff, if you are careful, you can get very, very precise approximations. The problem is you're most interested in your percentiles when stuff is not going smoothly. So when one of your servers is down or is serving just 200s really, really fast, or the distributions are very, very different, and then the averaging is just killing you. And here's like another example, which I prepared for this one. I am just averaging 1 hour percentiles over 24 hours for one data set. And it's not actually super terrible, but it's a 68% error between the true aggregated percentile in red and the blue average percentile. Yeah, that's true. You can see everything. Yeah, I think it's clear like this as well. Yeah, so, and the reason here is also what you can see is that the load for the different sections is different. So here you have like 35,000 requests in that hours, and here you have just 68. So it would be super stupid to average those two. At least you have to do a weighted average. You can do that. It goes back to 10% error here. But then remember, this is not actually what we are doing. We're averaging 1 minute bins, usually. So even if you look at a diagram like that, you usually see 1 minute measurements where you calculate the percentile, and then to graph it, you already average 1 hour. And then you have an average over very, very long times. So this effect only gets worse. So now that I stated the problem, I can talk about the solution. So there are 3 methods for that, and so one is to use log data, then one is to use counter metrics, and one is to use histogram metrics. So 3 ways. So via log data, that's really easy to explain. If you have the raw data for your time period you're interested in, you can just say, well, give me everything that was faster than the latency threshold and count it. That's fair. It's correct. It's clean. It's easy to do. The downside is that you have to keep your log data for, in this case, a month, because the reporting period for the latency SLO was 1 month, and typically SLOs are really praised in longer time periods. And the other problem there is it can get very expensive. And it can be very, very expensive. So a even mildly loaded API might easily do 200 megs, maybe even a gig of logs every day. A single metric is 10K bytes a day of data. So it's a whole different ballpark. Can do a ton of metrics if you are doing that. And there are like many vendors who do it, and I will say you can do sampling to somehow reduce the cost, and Liz will talk about how to do it properly tomorrow. I have also some experiments I will show in the class. Sampling on the nose doesn't really allow you to do latency percentiles. If you are clever about it, it might be fixable. but I haven't seen a silver bullet in terms of sampling where you get the latency percentiles also. Maybe it will be possible in the future, but I haven't seen it. So I mean, if you have all the data, you can for sure do it. But if you have not, it's not so clear for me. The second approach is countermetrics. So log data is done. And the idea is also very simple. So we have to know the threshold of our SLO before we're setting up the metrics. So we're picking the latency threshold up front, and then we count the requests that are faster than the threshold and store that as a metric. So instead of calculating a percentile value saying 90% of my data was faster than that, I just count how many requests were faster than the threshold I'm ultimately looking at. So it's kind of a reverse thing. So when I have this question, like how many requests does the 99% of the requests were served within 1 second, I can either look at the 99% or I can look at the 1 second. One is really looking at the percentile, but doesn't really work, or I can just count the number of requests that were faster than the threshold. I can count that every minute, and I can put it in a counter metric. And this, looking at it this way, allows you really to do efficient aggregation and correct aggregation. So it can just select all metrics you have for different nodes, then you can sum them up, and then you can integrate them over time, and then you will get accurate latency SLOs. So this is how it looks. You just count all requests that were faster than a second, and then you also, in black is the total requests, and in red is the bad requests, so the ones that were slow. And then do I have a laser? Yeah. So this line is the integral, so you do a cumulative count. So you just count how many total requests you had, and it goes up when the request rate goes up. And then at the very end, you read off the value. So here I have 10K, 100K requests, and 9K were bad. So you have 8.9%, which were slow, which is in your SLA, which is good. We wanted to have less than 10% slow requests. So it's easy, it's correct, it's cost effective because you're not storing terabytes of data in a Hadoop cluster. And you have full flexibility in choosing aggregation levels. You can select arbitrary time slices. You can select arbitrary nodes, so that's good. But you have to choose the latency thresholds upfront. And you don't usually, I mean, if you have an established SLO, you might have that knowledge, which are the thresholds which interest you. But oftentimes you're just guessing there. And so you pick a bunch. That's okay, but it's not that you can then later go back and change the SLO and say I want 110 instead of 100. I really have to live with the threshold that, that was provided. And Prometheus was already mentioned. They call this method a histogram method. So if you have a Prometheus histogram, then you have this LT metrics. This is also the nomenclature I used here. And they have means to process that as a histogram. Which is not wrong, but we have a, like when we talk about histograms, we mean something different, which is this guy here. So this is histograms, and in particular, we are interested mainly in HDR histograms. So just to brief recap, the raw data is listed below here. So this is all the individual samples I'm caring about here, and then I'm taking them into bins and counting how many requests I have in each bin. So this is just a minor difference is that I'm not counting how much requests were slower than 120, and I'm just counting how many requests were in that particular area, and I'm counting that. And the bin sizes are flexible here, and I will explain that in the next slide more carefully, how to do that best. But you already see in this range, I have much smaller bins than in that range. And the general idea is this works like floating point precision. So if I'm going way up, my bins get large, and if I'm close to zero, my bins are very small. So I have a fixed number of significant digits. So yeah, so the basic idea is you store your latency distribution in histograms, which are tailored for the operations domain. And the way HDR histogram does that is you choose a number of significant digits and you do everything with base 10 floating point numbers. So you have a total of 46,000 bins in the range from 10 to the plus minus 128. So that basically covers everything you might ever want to record. Like 10 to the minus 128 is smaller than everything you can measure, and 10 to the plus 128 is larger than everything I have at least encountered. And then you are spacing your bins in a way that you have a fixed like 5 to 10% accuracy. So you do bins at 10, 11, 12, then 100, 110, 120, and so on. So you always have a fixed number of significant digits. So here it's 2, there it's 2, there it's 2. Then you apply sparse encoding. So instead of recording 46,000 metrics and doing the counts in each bin, we're just saying, well, this is a blob for us, a binary bit, and we store it in a database which supports that. And then you can get away, even if you have 100K entries in a histogram, you're just hitting maybe 100 buckets, because usually your data is not spread against 10 order of magnitudes. It's confined within 1 or 2 orders of magnitude. So maybe you have stuff from 0.1 to 5,000, but that's only 3 orders of magnitude. So you'll have 300 bins roughly, which is not like really a lot of data. And then you can use it to do latency aggregation and accurate percentile stuff. So this has been, the HDR histogram has been developed by Giltini of Azure System. He has a magnificent talk about benchmarking and measuring latency and benchmarking, in particular GC latencies for Java. This is what he's doing. And we have a highly specialized, optimized C and like 5 other languages implementation, which does exactly that. It's called CircleHist. And it's one of the things we base Circonus monitoring product on. So here's how it looks. This is the latency data spread out over, this is half a day. And for each minute, you have a full histogram. So we visualize it as a heat map, but this is the more traditional visualization. And then you can do latency SLOs with histograms very conveniently. You just capture all latency information as histogram metrics. You aggregate those latencies over nodes and endpoints. Because you're now aggregating the histogram, this is very easy. If you have 2 histograms with the same binning, then you can just aggregate the counts. Very straightforward. And then you can just count how many samples are below the thresholds to compute your SLO. And I might be able to demo this. So we can flip that into a histogram summary mode, and then we can say, well, give me for the last 4 weeks the full latency distribution, and they can say, well, 50 milliseconds was here. This was what I was interested in. And yeah, we have a UI glitch. But here in that case, for 47 milliseconds, it would be 11 million samples were below that. And we had a total of 13 million samples, and that would be 88.7%. And I can even go back a year. That will take a little while to render. And then I can zoom in, yeah, USENIX. And yeah, let me reload that real quick. Yeah, this is, again, this is a year worth of data, and I'm now zooming in at some data we collected in March. And then I can say, well, flip this into histogram summary mode, and I can evaluate the SLA here and say, okay, below 30 seconds, I had 96% of the data. So this is how you can do it with histograms. And it's fairly convenient because you have full flexibility in thresholds, you have full flexibility in choosing aggregation levels and intervals, and it's cost effective. The downsides is you need HDR histogram instrumentation. We have libs for that, and Envoy Proxy recently started using it, and we're seeing more and more uptake of that, and people building HDR histogram instrumentation in. And you need a histogram data store who does it. I mean, you can obviously use our products, but there's maybe some uptake with other backends which also support that. And actually, for this talk, I'm particularly excited to see that there is actually a movement in that area. So there are more competing technologies which are actually doing very similar things. So we have, our stuff dates back to 2013, then we have HDR histogram for 2015. There's now a DD sketch for a distributed distribution in 2019. It's a paper a few months back. It's from people working at Datadog, so I have some suspicion that the DD might have a double meaning there. They're calling it a sketch, but what it really is a histogram. And they are using logarithmic bins, not log linear bins with base 10. They are using logarithmic bins with like a base of 10 to the 1 to the 0, 1. So that you approximately get the same resolution we had here. So you might, if you're a Datadog customer, be able to use similar technology as well. And it's just, in general, exciting to see people acknowledging the problem and building technologies that allow you to address this stuff. I have also, for this thing, did a little benchmark of all those tools. So Circonus, HDR, tdigest, it's another, that's a clustering method, but it's doing the same thing. And the DD sketch, they all nail the accuracy part. Like, this is not 10% error. This is 0.01% error or 0.25% error. So they all pretty much nail it. And then performance, I mean, this was a very rough benchmark where our stuff was very favorable, but it doesn't really, I mean, this is all pretty good performance. At least the sketch and the circle hist are doing very good. So that rounds it up. Thank you very much. And yeah.
Heinrich, this was awesome. Tomorrow we have 3 hours of statistics workshop with Heinrich. So we will have an opportunity to follow up on this and ask a lot of questions, but we ran out of time. So if you have questions which can't wait until tomorrow, just catch Heinrich in the corridor. And we will start next session in about 4 minutes.
Thanks.